will speak on Ved will speak on non-linear conditions and sorry, I'll say that again. Let me wait till the screen is shared. Okay, yeah. So Ved Datar from IISc is going to speak about non-linear PDEs and positivity conditions in algebraic geometry.
All right. I'd like to thank Siddharth for the introduction and would like to thank the organizers for the opportunity. Yeah, perhaps maybe I should, to appear less unfriendly, I should, I think, switch on the video. Jesus, how do I go?
See it somewhere at the bottom, there'll be a mute and start video button.
Yeah, I can, oh, I have to. No, so somehow I've lost the Zoom window.
Yeah, Zoom does these things.
I
You have
can
a
only...
PDF window in front of you, right?
Oh, yeah, okay. Now I get
You got it.
Okay. Yeah, okay.
You still look unfriendly.
Yeah, I'll try to smile as much as I can. All right. So, yeah, so I would like to thank the organizers. And of course, yeah, funnily, I mean, I'm representing IISc in this sort of joint seminar, but I'm actually just a few kilometers away from IISc Pune right now. But so I'm going to talk about a class of PDEs that's quite important in Scalar geometry. They're called inverse Hessian equations, or as Vamsi would
you
prefer.
Have to make your PDF full screen, sorry.
Yeah, I'll do that. Or as Vamsi would prefer, they're called generalized Monge-Ampere equations. And the key is I'm going to talk about this relationship to some very nonlinear positivity conditions in algebraic geometry. So here's an outline of my talk. I'll first talk about the Scalar cone and this classical Nakaya criteria on characterizing the Scalar cone. So that's really where this story begins. I mean, with the Nakaya criteria, there are no PDs involved, but then a generalization of the Nakaya criteria very remarkably involves an important PD in complex geometry. I'll then talk about inverse Hessian equations, and I'll give a survey of some recent breakthrough due to Gauchen, and then I'll mention a joint result with Vamsi. And then if time permits, I'll sort of speculate a bit and also talk about some ongoing problems that I'm interested in. Okay, so since some of you, I mean, might be the Riemannian crowd, let me just quickly give an overview of Scalar geometry. I guess Harish has already done some of the heavy lifting. So I'm going to start with a compact complex manifold of dimension n, and of course it's going to be without boundary. Then we have this standard picture that in the neighborhood of each point, we have holomorphic coordinates. And so just to fix some notation, I'm going to put the real and imaginary parts as x and y. Then useful sort of viewpoint is to actually talk about the almost complex structure, which is an endomorphism of the tangent bundle. And you can define this using this simple formula. And it turns out that this definition is actually independent of the choice of the holomorphic coordinates. And this is essentially equivalent to the Cauchy-Riemann equations. Again, in fact, conversely, if you have such an almost complex structure which satisfies some sort of an integrability condition, then you basically have a much more sort of complicated version of the Frobenius's theorem, namely the Nylander-Nirenberg theorem, which tells you that you can conversely also find holomorphic coordinates so that J is given precisely by this. So that means giving the data of a complex manifold is actually equivalent to giving a data of this almost complex structure satisfying some additional integrability conditions. So I'm actually going to talk about a subclass which are called as Scalar manifolds. So this triple is called a Scalar manifold if G is a Riemannian metric which satisfies this, which is in some sense compatible with J, So then we call G a Hermitian metric. And moreover, most crucially, the Kähler condition basically says that J is parallel with respect to the standard Levi-Civita connection. So in terms of holonomy, what this says is that the holonomy is contained inside the intersection of GLNC with SO2N. And I should have written that out. This intersection is basically just the unitary group of n dimensions. Right. So in that sense, scalar geometry is basically like the intersection of complex geometry and Riemannian geometry. Okay, so that's why I mean this is a beautiful field where you can borrow techniques from Riemannian geometry, like this. I mean, Harish, for instance, mentioned the Cheeger-Colding theory and so on. All of that can be adapted to Kähler geometry. On the other hand, you also have algebraic geometry that plays a role via this holonomy group of GLNC. Okay, and that's why you can prove many beautiful results, because you have these techniques from these two vast areas of math. So actually, instead of focusing on the Riemannian metric, in Kähler geometry, it is more customary to focus on this form that is concocted out of the Riemannian metric. So this is a real positive 1-1 form. Locally, you can write it in this form, where this Gij bar is a Hermitian positive definite matrix of functions, right? And in fact, the Kähler form determines G completely. And so, as I just said, it's customary in Kähler geometry to, instead of considering this triple, to actually consider this particular triple, right? So forget about the Riemannian metric, but focus on the Kähler form instead. And so I'll abuse language and sometimes also call omega as the Kähler metric. Okay. And then in fact, the Kähler condition is actually equivalent to this form being closed, right? So this puts severe topological restrictions on Kähler manifolds. So for instance, any random complex manifold might not admit a Kähler metric. Okay, so I'll talk about an example in a minute. So then, given a complex manifold Mj, the natural question is, does it actually admit a Kähler metric? And if so, how many of them, right? So of course, how many of them needs to be made more precise. But that's one of the important questions that is that has been studied over the years in Kähler geometry. So let me just quickly give you some examples. So the first sort of family of examples is when you have complex dimension 1. So you're basically working with Riemann surfaces, and then Riemann surfaces always admit a Kähler metric, right? So in fact, you can simply take a compatible Riemannian or rather a Hermitian metric and just take its area element, right? That will give you a Kähler form. Then the sort of flat model in this subject is basically Cn with the standard Kähler form. So if you look at the corresponding Riemannian metric, this will just be the usual flat Euclidean metric on R2n, which is of course isomorphic to Cn, right? Then, as Harish mentioned, the model in the positively curved case is this complex projective space with the Fubini's 2D metric. And then it's a simple exercise, I mean, almost trivial exercise, that if you have complex submanifolds of Pn, then this omega Fubini's 2D actually induces a Kähler form on these submanifolds. They're also called subvarieties, non-singular subvarieties. And then all of these will be Kähler. So as soon as you have subvarieties of Pn, they're all Kähler, right? Now you might wonder if that sort of exhausts the lists of all Kähler manifolds. The answer is no. And in fact, some very sort of simple examples turn out to be non-projective. Sorry, I mean, you might, right, you might ask whether there are examples of sort of non-projective Kähler manifolds. And it turns out that a generic torus, so you take a lattice in Cn, and then on the quotient, you'll have an induced flat metric. It turns out that, I mean, for this generic lattice, the corresponding torus actually is not projective. Of course, you have to restrict to higher dimensions, because in dimension 1, they're all elliptic curves, and all elliptic curves are projective. Right. So then as I said earlier, you might ask whether all complex manifolds are Kähler, and the answer is again no. There's this very important class of counterexamples called as Hopf surfaces. I don't want to go into the definition of these, but it gives you a whole family of complex surfaces that are actually not Kähler. So these are two-dimensional complex manifolds. As I just said earlier, in one dimensions, you cannot find any counterexamples. Okay, so then I want to talk about an important invariant of a Kähler manifold, namely the Kähler cone. So remember, I said that the Kähler condition, which means that the J is actually parallel with respect to the Levi-Civita connection, is actually equivalent to omega being closed. This implies, so this chi should be omega. This implies that this chi basically determines a cohomology class in the second de Rham cohomology. And also, because it's a 1-1 d bar closed form, it also determines a cohomology class in this 1-1 Dolbeau cohomology group. So I'll denote the intersection of such classes by H11 of MR. So that means you, given a Kähler form, you basically get a representative in some cohomology class. So then we say that a class in this space is called Kähler and write it as alpha is positive if there exists a Kähler form omega in alpha. Okay, so then the Kähler cone is basically just the set of all 1-1 cohomology classes that are Kähler. And it turns out to be an open convex cone. And of course, this Kähler cone is non-empty if and only if MJ admits a Kähler metric, right? Because then that will give you one, the corresponding cohomology class will give you one element in this cone. So actually this Kähler cone is a very interesting invariant. And in fact, for instance, one version of mirror symmetry can, the mirror symmetry conjecture can be approached by studying degenerations of Ricci flat Kähler metrics as this class of your Kähler metric approaches the boundary of this Kähler cone. Similarly, singularity formation of the Kähler-Ricci flow is also determined by sort of going to the boundary of this Kähler cone. So this turns out to be a very important object in very sort of different areas of complex geometry. So one remarkable fact which makes scalar geometry much more tractable than Riemannian geometry is this so-called DD bar lemma. So this says that suppose you take any two representatives in a particular 1-1 class, 1-1 real class, and suppose the Kähler cone is non-empty, that means you're on a Kähler manifold, then actually there exists a real valued function such that the difference is given by the DD bar of some of that real valued function. So notice that if they belong to the same cohomology class, they basically differ by the D of a 1 form, right? But the fact that you are actually on a Kähler manifold and the fact that these are 1-1 classes actually gives you something a little bit extra. And the proof is basically via the refinement of the Hodge theorem in the Kähler setting. Okay, so it turns out, for instance, the Einstein equation in Kähler in Riemannian geometry is extremely intractable. So much so that, for instance, there were no known examples of Ricci flat Riemannian manifolds which were not whose sectional curvature was not identically zero until basically Yaos produced examples of Kähler manifolds which are Ricci flat and which are not, whose sectional curvature is not zero. So it turns out that because of this DD bar lemma, the Einstein equation, for instance, which is a tensorial equation in Riemannian geometry, actually reduces to a scalar equation in Kähler geometry. So that makes Kähler geometry much more tractable, and all of that basically boils down to this very sort of simple lemma that is taught in any first course on complex geometry. Okay, right. So to just give you a sense of how this Kähler cone looks, I'll give you a couple of examples of the Kähler cone. So if you look at a Riemann surface, then the second cohomology group is basically one-dimensional. So the Kähler cone is simply the positive part of that real line. So it's the set of all, I mean, it's isomorphic to a set of all positive real numbers. So you can easily see that this is an open convex cone. A non-trivial example is if you blow up P2 at a point, then it turns out that this H11 planned by, I mean, you can think of this P2 blow when you blow up a point, you introduce an additional representative in the cohomology space, which is namely the exceptional divisor. And it turns out that H11 is basically just spanned by these two in the case of P2 blown up at a point. And then there are various criteria. You can either apply Seshadri's classical criteria or Nakaya criteria, which I'll get to in a minute. And you can show that this Kähler cone is basically given by those cohomology classes B times H minus A times E, such that B is bigger than A is bigger than 0. Okay, so pictorially, I mean, you can represent it as sort of this cone, one of whose sides is the y-axis, the other side is the axis, is the line x equals y, right?
Sorry, Ved, I had a quick question.
Yeah.
Calling it Kähler cone, but symplectic form I can see, but why is it obvious that it's a cone at all? That is convex linear combination of Kähler forms is a Kähler form, or?
Right, because you have positivity, right? So, I mean, you need something that's symplectic, which is d omega is 0, but you also need that if you write down the Riemannian metric, I mean, if you look at omega of, let's say, x comma jy, that has to be positive, right?
That's right. So that's why you can't have this and negative. But what I'm saying is if I take two things, why is everything in between in the cone?
For the same reason.
For the same reason, right? Because you just take t times alpha 1 plus 1 minus t times alpha 2.
Okay.
Right. And you have a representative in alpha 1, let's say omega 1, a representative in alpha 2, omega 2.
Okay. So the linear combinations will give you a Kähler form.
Yeah, the
same complex
linear,
structure.
yeah, exactly.
Okay, fine, thanks. Yeah.
Right. So, so next, let me at least state what the Nakaya criteria is. So this gives a characterization of the Kähler cone. So let's say you take a p-dimensional subvariety of M, and let's say you have a Kähler class, let's say alpha, which is the cohomology class associated to the Kähler form omega. Then you can construct, you can concoct some sort of a volume of this subvariety. So by definition, this is precisely this. And by definition, this is basically just integrating out omega to the p on the regular part of V, right? So then there's a elementary calculation, which you can find in Griffiths and Harris, that basically Stokes' theorem holds in this setting, which means that if you choose a different representative omega, you still get the same answer for the volume, okay? So this is indeed an invariant of the class. So now let's say I take a 1-1 class, then the Nakaya criteria is the following. So you restrict to only projective manifolds now and restrict to an alpha that comes from the first Chern class of a line bundle. Then the Nakaya criteria says this belongs to the Kähler cone if and only if the volume is positive for all possible choices of these varieties. So this is a very useful criteria because to test whether there is a form that is pointwise positive is actually hard. On the other hand, the volume is a topological thing, right? I mean, you can calculate it using intersection numbers essentially, and which is what you do in the second example of the blow up. You basically just have to compute the intersection numbers to decide what lies inside the Kähler cone. So because the volume is a topological thing, this is much easier to verify than actually trying to find a form that's pointwise positive. Okay, so this gives you a very practical way of deciding whether a 1-1 class actually lies inside the Kähler cone or not. Now, in the late 90s and early 2000s, Demey and Pon actually generalized this to all Kähler manifolds. And in fact, even in the projective case, they basically also removed this condition that alpha has to be the first Chern class of a holomorphic line bundle. So they generalized this in two directions. But then you have to actually, it's not enough to just consider the volume. You have to basically consider these intermediary sort of intersection numbers. So suppose chi is a background Kähler metric and alpha is a 1-1 form. Then you have to check that all of these intersection numbers have to be positive for k going from 1 to the dimension of your subvariety. Okay, so it turns out that if M is projective, then because you can assume that, I mean, by choosing a suitable sort of Kodaira embedding, you can assume that chi is actually given by essentially the first Chern class of the hyperplane bundle. You can actually reduce this to the computation of a volume on a lower dimensional subvariety. So in the projective case, you actually recover the Nakaya criteria from the Demey and Pon criteria. Because you might ask whether, I mean, in the projective case, this seems like Demey and Pon are assuming something more than what was assumed in the Nakaya criteria. But it turns out that because you have this hyperplane bundle in Pn, you can actually, I mean, this condition is equivalent to the volume condition when M is projective. Okay. And what is quite remarkable is that the Demey and Pon proof actually uses Yaos solution to the Calabi conjecture. That means it uses the solvability of the complex Monge-Ampere equation. So these are you look at the complex Hessian and you specify what the complex Hessian should be and solve for the unknown scalar function phi. Okay. So
with one small confusion.
Yeah.
So alpha should has some Kähler representative, but chi is like one fixed Kähler.
Yeah. So you can remove that. I mean, you can let instead of chi, you can take any Kähler class. That's enough.
Okay.
Right. Was that your question?
Yeah. I mean, there seems to be two Kähler forms or something in this, right?
Exactly. So alpha is a class and chi is a background Kähler form. But you see that this integral actually depends only on the homology class of chi anyway, right?
Okay. Yeah.
So that's what is important. And that's what, as I was saying, instead of chi, if you're on a projective manifold, you can actually just take, instead of chi, you can take the homology class of the hyperplane bundle, basically.
No, Ved, I mean, what if I change chi to some other Kähler form, not in the same cohomology class? Still, it shouldn't matter, right?
I mean, yeah, it doesn't matter. You should still have something that's positive, right? So this only depends on the positivity of this, right?
Oh, yeah. Okay. Right. Chi will appear here. Okay, fine.
Yeah.
The condition will also change.
Yeah. So I mean, the numerical values will change, but the sign will not change. I mean, it doesn't matter what Kähler form you pick.
Yeah.
Okay. And of course, if you pick it in the same cohomology class, then of course even the values
won't change. Yeah.
So So as I was saying, I mean, quite remarkably, this actually uses the solution to these very complicated complex Monge-Ampere equations. So let me just outline the proof of Demey and Pon, which tells you where this. Actually, how many minutes do I have? Maybe I can. So I have around 15 minutes, right?
Right, little less than that.
Little less than that. Okay.
Yeah.
So right. So maybe let me just mention that so Yaos theorem basically enters via this so-called concentration of mass. So what this says is that suppose you take a class on a Kähler manifold such that somehow it lies on the boundary of the Kähler cone. So there are various ways of saying in what way it lies on the boundary. One way is you just take this Kähler metric and add t times that Kähler metric and add it to your class that lies in the Kähler cone for all t positive. And you also need this sort of bigness assumption, which means that the volume, the total volume of m tilde with respect to this class is positive. Then the concentration of mass says that for any codimension P subvariety Y, there exists a PP current theta, which will actually be bigger than some positive constant times the current of integration along Y. So that means even though this is not a Kähler class, so I should say that there is, right, so even though this is not a Kähler class, you can still find a suitable current that basically is a non-negative current, and it puts some mass on some subvariety. Okay, and how is this theta related to this alpha tilde? You'll see that this theta is actually going to be some omega tilde to the p, where omega tilde lies essentially in this class alpha tilde. Okay, and to find this current theta, you basically have to solve a certain Monge-Ampere equation. So you take a sequence, a family of reference forms that concentrate along your subvariety, and then by Yao you can find a corresponding set of omega t tildes which solve a certain Monge-Ampere equation, and then you can show that these actually converge to a current, at least subsequentially. The point is that unless you solve a certain PDE, there's no reason why such a random sequence of currents will actually converge to some nice current, right? So for that you have to solve some PDE, and that some PDE turns out to be Yao's equation. Okay, so maybe I'll move on to the inverse Hessian equations. So a question of central interest in Kähler geometry is to construct constant scalar curvature metrics. So there is a very fundamental conjecture in the field called the Yao-Tian-Donaldson conjecture. So this says that there exists a Kähler form whose scalar curvature is constant if and only if this pair is stable in some sense. Okay, so modulo some results in algebraic geometry, there has been substantial progress on this conjecture in recent times. But I want to talk about the variational aspect of this conjecture. So if you fix a reference metric in your class alpha, you can concoct a certain energy, which is called the Mabuchi energy. So it has a principal term which essentially looks like x log x, if you interpret this correctly. But then there is also a correction term that involves a certain functional. That functional can actually be defined with respect to any background 1-1 form, any background real 1-1 form. And it can be characterized by this variational formula that the first variation of that functional is given by the first variation of the scalar that you are varying times whatever is there in this bracket. Okay. Right. So let me rewrite the variational formula for this J functional. So clearly a critical point for this J functional basically satisfies, what is the Euler Lagrange equation of this J functional? It's basically this. Here omega phi is basically just omega naught, my reference metric, plus dd bar of phi. Okay. So the Euler Lagrange equation gives you this equation. Why is this equation useful? Because if you assume that this reference form is actually Kähler, which means chi is positive, then it turns out that the above functional is actually convex on the set of these potentials phi. And moreover, if there is a solution to this equation, it turns out that this functional is actually lower bounded. Okay, so why is this useful? Because if your manifold is of general type, which means that the first Chern class is negative, then by Yao, you can actually take chi to be the negative of the Ricci curvature of some reference metric. This is just by Yao's solution to the Calabi conjecture. And now, why do I do this? Because in the formula for the Mabuchi energy, you have the J functional with respect to minus Ricci omega naught. So then if you're able to solve the J equation in the appropriate class, then it will turn out that this J functional is bounded below. And hence, by this was a well-known fact, observation due to Tian, that the K energy will actually turn out to be proper. And then once you have a proper functional, it will turn out that minimizers to this some abstract infinite dimensional nonsense. Actually, it's a deep work. I shouldn't say nonsense. It's due to Tamash, Darvas, and Rubinstein. It will tell you that this functional will actually have minimizers. And then some very deep PD result will tell you that this minimizer will actually be a smooth CSCK metric. Okay, so at least for manifolds of general type, solving this auxiliary equation will actually help you solve the CSCK problem. So that is why this equation is important. So let me rewrite this equation. This is the so-called J equation. So trivial necessary condition is obtained by just integrating both sides. So that will decide what value of this constant should be. Now, suppose n is equal to 2, that means I'm on a complex surface. Then, in fact, you can just complete squares and reduce the J equation to a complex Monge-Ampere equation. And so then by Yaos' solution to the Calabi conjecture, a necessary and sufficient condition is that the class of this sort of background form, omega naught minus C1 by 2 times chi, is actually positive. Okay, so then if you combine Demai and Pon with Yao, this tells you that for complex surfaces, solvability of the J equation can be actually reduced to some numerical conditions. That means you have to check that certain intersection numbers are positive. Okay, so at least in dimension 2, you can reduce the solvability of this equation to checking some numerical conditions, which, as I mentioned previously, is a much easier thing to do. Okay, so now let's try to understand what happens in higher dimensions. So in higher dimensions, it's actually useful to sort of rewrite this equation in terms of the eigenvalues of chi inverse times omega phi. So locally, you should think of omega phi as given by some Hermitian positive definite matrix. Similarly, chi is locally given by some positive definite Hermitian matrix. So you can take chi inverse times omega phi. That's going to be a positive definite Hermitian matrix. So it'll have eigenvalues which are real and positive. Then the J equation will basically translate to this equation. So you have 1 by lambda, the sum of the reciprocals of the eigenvalues is specified. Okay, so if you drop one of the eigenvalues, which might seem like a silly thing to do, but if you drop one of the eigenvalues, then of course a necessary condition is that the resulting sum of reciprocals is actually strictly smaller than the right-hand side. But so even though it might appear to be a silly thing to do, it turns out, you can rewrite this in terms of positivity of some n-1, n-1 forms. So globally, that just means that this n-1, n-1 form is positive. Okay. So that gives you a necessary condition. Unfortunately, the above positivity condition, which we'll call the cone condition, is almost as hard as checking the equation itself. Okay, but even so, it turns out that this necessary condition actually is a sufficient condition in solving the J equation. So this is the main, the fundamental theorem in this area. So the following conditions are equivalent. Firstly, you want to solve the J equation. And of course, as I said, a necessary condition will be that this form is positive. Right? But then it was proved by Song and Weinko in 2009 that this cone condition also turns out to be a sufficient condition. So this is a purely PDE result, that if you have a certain pointwise positivity, you can solve a certain PDE. And for people familiar with this subject, this cone condition is in some sense a sub-solution for the PDE that we are trying to solve. Then about 2 years back, Gauchen in quite a remarkable paper proved that you can actually replace this pointwise condition by a numerical condition. Okay, so that's this point number 3. So I should mention that this was already conjectured by Lejmi and Zeklihidi, that you can replace the pointwise condition by a numerical condition. But Gauchen actually proved something a bit weaker than what the full Leibniz-Euclidean conjecture was. In that he had to assume that you have some sort of a uniform positivity. That means you have these intersection numbers, instead of them being just positive, they have to be bigger than some epsilon times these volumes. Okay, so he had to assume some uniform positivity. And actually the full Leibniz-Euclidean conjecture was without this uniform positivity. Just that some intersection numbers are positive, then that should imply that you can solve a certain PDE. So about, I guess, almost exactly a year back, Vamsi and I were able to extend Gaussian's work, at least for projective manifolds. So we actually looked at a more general class of PDEs. So you take these n-1 non-negative real numbers such that at least one of them is positive, and you have to have, of course, a necessary condition that the volumes on both sides of the PDE that we are trying to solve match up. And we looked at the so-called generalized Monge-Ampere equation or inverse Hessian equation. So of course, notice that if C1 to Cn-2 is 0, then this actually reduces to the J equation. Okay. And then we proved that the following conditions are equivalent. Firstly, the PDE that we are trying to solve has a solution that's equivalent to a certain pointwise positivity condition holding. So this is again, this was a PDE result, which essentially, was already known through some works of Zekliidi, Collins, and other people. I guess Bogwan, and then Vamsi himself had some results in this direction. So the PDE result, we had to improve the PDE result a bit also, but that was essentially known. Our main contribution was that you can replace the pointwise positivity condition by a numerical condition. And notice that our numerical condition is actually just pure positivity, not uniform positivity. Okay, so on the other hand, the trade-off was that we had to assume that our manifold is a projective manifold. So our techniques work only for projective manifolds. Okay, so let me maybe end with some remarks that in particular, we obtain a stronger version of the theorem of Gaussian, at least when M is projective. The reason why we looked at generalized inverse Hessian equations is not because we just wanted to sort of extend Gaussian's result to a slightly more general class. That would have been boring. But in fact, there was a well-known conjecture of Leibniz and Zekliidi on the solvability of these sort of intermediate inverse Hessian equations. And they had conjectured that this should also be related to some numerical condition. And of course, when k is equal to n-1, this is the J equation. Now, it turns out that as of now, Gaussian's method, should be extendable also to these equations, but that's not yet known, right? So the full Leibniz-Euclidean conjecture was still unsolved even after Gaussian's work. And of course, as I said, Gaussian assumed uniform positivity. On the other hand, we had to assume only strict positivity. And in the projective case, we actually ended up solving the Leibniz-Euclidean conjecture. Another sort of side remark is that we also obtain an equivariant version, which means that if you have a group action, then you get solutions that are invariant under the group action. And the key point is you have to also test this numerical condition on a much smaller class of sort of invariant subvarieties. And this actually recovers earlier results of Collins and Zekliidi on toric manifolds. And then finally, I should remark that Jian Song has removed the assumption of uniform positivity for the J equation, even for all Kähler manifolds. So we could only do it for projective, but he has now managed to do it for all Kähler manifolds. But that still leaves the full Leibniz-Euclidean conjecture for these intermediate inverse Hessian equations, or for the kind of inverse Hessian equation still open, whether you can actually prove an existence result on general. Okay, so right, so maybe I'll skip this, and my first sort of future direction, maybe some students can take this up, was that it should be possible to extend my result with Vamsi to general sort of Kähler manifolds, right? So maybe I'll end it with this. These are the sort of select references if you want to go back to read some more about this. And yeah, thank you for your attention. Sorry, I went over time by a few
No, that's
minutes.
fine. That's fine. Thank you very much. Very nice. Yeah, let's thank the speaker for this. So, are there any questions? I had a quick one. How do you use projectivity? What is it you use about?
Right. So, so the point of that is, so maybe let me just quickly go back to the Demy and Pon result. So there's this, sorry, because of this pause function. Yeah. So the key point in the Demy and Pon method was this concentration of mass. Now, in the projective case, one can actually simply take this m tilde to be m itself. And why? Because there are lots of subvarieties, lots of ample subvarieties. One can just try to concentrate mass along a subvariety, which is obtained by intersecting the hyperplane bundle with m. But for instance, if you're trying to do this on a complex torus, there are actually no subvarieties to work with, right?
Right.
So then one cannot, I mean, how do you apply this concentration of mass technique? So then there's this very beautiful and elementary trick of Demy and Pon. You basically take m tilde as the product, then the product has a canonical subvariety